Okay, let's take this example. Number 1, a fluid having a kinematic viscosity equal to 4 times 10 to negative 5 meters squared per second flows in a 750 meters long pipe having a diameter of 20 mm. Determine the head loss required to maintain a velocity of 3 meters. So here, you have first to list down the given. Okay? So given are the kinematic viscosity, the length of the pipe. Okay, you have 4 times 10 to negative 5 meters squared per second. Then for the length, you have 750 meters. Then for the diameter, you have 20 mm. Then for the velocity, it is 3 meters per second. You are going to find the head loss. Okay, the head loss. So here, this is the solution. So we know that the head loss, the formula of the head loss is this one, FLB squared over D2G. And we need to find the value of, we need to have a value of F. So F can be, based on the given, F can be taken when you determine the Reynolds number. So in determining the Reynolds number, we can identify what type of flow so that we will know the formula in getting the friction factor. So because we have laminar flow and turbulent flow based on its Reynolds number. So since in this problem the Reynolds number is 15 and it is less than 2000, so it means that the flow is laminar. So F, we will use the formula of the friction factor. F is equal to 64 over Rn. So that's why we have our head loss 734.518. I hope you understand, okay? Number 2, fluid flows through a 20 mm diameter pipe, 100 meters long at a Reynolds number of 1,750. Calculate the discharge if the head loss is 175 meters. So in this case, we know that the Reynolds number is less than 2,000. So we can directly judge that the type of flow here is laminar. So I will advise you to list down all the given. So for the given, we have the diameter, you have 2 mm. Then Reynolds number, you have 1,750, and this is less than 2,000. Then the discharge is 175 meters. So you can directly substitute the values to the formula because we need to determine the discharge. Is it the discharge? Sorry. The given is head loss. Okay, 175 is the head loss. And what we are going to find out is the flow rate, the Q. So you can directly substitute it to the formula. So the value of Q is equal to 0.00111 cubic meter per second. So you have to remember in this topic, you need to list down all the given. So if the problem, Reynolds number is given in the problem. So you can think that the head loss we're going to use is the formula of Darcy, because the friction factor is also be taken when you have when you have the Reynolds number, and you can determine the type of flow. Okay, for number 3, the given again. For the given, you have the specific gravity of oil. You have 0.95. Then Q is 2 liters per second. So you have to convert this into metric. So 1,000 liters is equivalent to 1 cubic meter. So you have 0.2 cubic meter per second. Okay, then another given, you have your F value 0.0225, and you need to find the head loss, then the pressure drop. Okay, then the pressure drop. So pressure drop can be P1 over gamma minus P2 over gamma, which is equal to the change of the pressure. Okay, change of the pressure head, and it can be P1 minus P2, which is equal to change of pressure. So first we have to determine the head loss. So given F is given, so you can substitute directly to the equation because Q is also given. The diameter, diameter is also given. So D is equal to 200 mm. Then you also have the length. You have the length 500 meters. So you can directly determine the head loss. But here, the head loss we considered is only the friction factor. The head loss is only the major loss due to friction. Okay, because there's no pipe fittings in the problem. There's no bending of the pipe. There's no sudden enlargement of the pipe. So we only have head loss due to major losses. Okay, so here, if this is our equation 1 and this is our equation 2, so you write the energy equation between 1 and 2. So you have, okay, so sometimes don't be confused with the H as a symbol of total head and E as a symbol of total head, because some of the references mostly used also E as the symbol of the total head, as long as you know what do you mean by the total head. So in this problem, it uses E. So here for the equation 1, we have energy equation 1 is equal to energy at equation 2 plus summation of head loss. So your head loss is equal to minor loss and major loss. Okay, minor plus major, but you don't have the minor losses, only the major losses. So you have H2, okay, plus head loss, which is major loss. Okay, so what is the formula of E1? E1 is equal to P1 over gamma plus Z1 plus V1 squared over 2G. Same as E2, you have P2 over gamma plus Z2 plus V2 squared over 2G. So, you can have this equation. Then, since they are the same pipe, no, in section 1 and section 2, so your velocity, and you have the same Q discharge, so your velocity at V1 and V2 are equal, so that's why it will cancels out. Okay, then what you have is the pressure head, because this is just a cut of the section, no? You just cut the pipe. That's why you have section 1 and section 2. So you have pressure there. So you have P1 over gamma plus, okay, you have here, there, the head loss. The head loss is this one, that is 86.82. Okay, it is given, no? It is given that the pressure drop is 10 degrees in the direction of flow. So the angle is given. So that's why the difference of the energy, and the total energy between section 1 and section 2 is equal to head loss. So you have here P1 over gamma plus 86.82 minus, okay, friction loss 116.2 is equal to P2 over gamma plus 0. So you have here the change of pressure head is equal to 29.38 meters of oil. So you have to remember that is meters of oil. Then multiply it to the specific weight of the oil in order to determine the pressure drop. So the answer is 273.81 kilopascal. Okay, so I hope you got it. Okay, so number 4. Okay, oil with a density is equal to 950 kilograms per meter cube, and viscosity, that is kinematic viscosity, 0.0002 meter squared per second, flows through a 300 mm diameter pipe that is 100 meters long with a head loss of 8 meters. The relative roughness is equal to 0.0002. Okay, calculate the flow rate. So here again, I try you to list down what are the given. So you have 950 cubic meter per cubic, okay, kilogram per cubic meter. Then the kinematic viscosity, you have 2 times 10 to 1, 1, 2, 3, 4. Okay, negative 4. Okay, 1, 2, 3, 4, 5, I guess. Is it 5? 1, 2, 3, 4. Okay, 1, 2, 3, 4, 5. Okay, 5. Okay, and this is meter squared per second. Then the diameter is 300 mm. Okay, so you also have the length, which is 100 meters long. Head loss is equal to 8 meters. The relative roughness is equal to 0.0002. Calculate the, okay, sorry, these are the given. Okay, Okay, you are going to find Q. Okay, so since the relative roughness is given, and the length, the diameter, the viscosity, the density. So from this equation, for your solution, you can find you can have this equation. Your equation will be in terms of FB squared is equal to 0.471. In the equation, in getting the Q, since Q is not given, so it is difficult to determine. That's why we need to do trial and error. See, if Q is not given, you don't have the velocity. If velocity is not given, you cannot determine the Reynolds number. If you don't have the Reynolds number, you cannot determine the friction factor. So, we have to do trial and error this time. Our equation is in terms of, okay, this will be our equation 1, FV squared is equal to 0.471. Okay. In this in this problem, you can try any value of f. You can try 0.01, you can try 0.02, you can try 0.04. It's up to you. As long as you can get the right answers. So your first trial, you have a different initial trial. You can try that in your home. But here, we will try f is equal to 0.03. So, substituting the value of f to the equation 1, okay, so equation 1, you can get the velocity. So, that is equal to 3.962. So, once you have the velocity, you can get the Reynolds number. So, Reynolds number can be also like this, NR or RN. So, those are the symbol. Okay? Then, once you have the Reynolds number, since you also have the relative roughness, it is given and this is already computed, you can find again the value of F. So, that using Colebrook-White equation. Okay, so why? Because the Reynolds number here is 59,430 and that is greater than, much greater than 2,000. Okay, so since this is the computed F, it must be that the computed F is equal to the assumed F. So this will be your assumed. So it must be computed F equal to the assumed F. So in this case, F equal to 0.0206. This is not equal to the assumed. Okay, which is 0.00. Okay, 0.03. Okay, 0.03. Okay, so the computed F now here, your computed F, this is computed F, we will use this again as our second trial of F. So you have new trial, so F is equal to 0.0206. Then substitute to equation 1. Okay, you substitute this into equation 1, you can determine the velocity. Then, for the velocity, you can also determine the Reynolds number, and this is greater than 2,000. Sorry, this is greater than 2,000. So, it is turbulent. So, again, you use this equation. Then you have F. This is now okay. So I guess there's wrong, no? There's wrong of the computation. So I like you to continue this one in your notes, okay? So there's no, because here you try to get the answer following the following the procedure. So you try if this is equal to 0.019, no, after substituting this equation 0.019, then you try again. So this is the computed, and this is not equal again to the assumed F, which is 0.0206. Maybe there's a missing solution here. Try again. Okay, try again. F is equal to 0.0199. Then you have to get the V, then Reynolds number. Maybe that time they are okay. So the computed F is 0.0199, okay, is equal to the assumed F 0.0199. So that's the time you have to stop, meaning that the velocity is equal to 4.865 meter per second. Then substitute it to the formula. Q is equal to area times velocity. So the answer is 0.344. I like you to check this, okay? So please check the solution. Then follow the procedure. Okay, for number 5, given, you will have to list down the given. Your density is 680 kilogram per meter. Then you take note that the pipe is smooth, so your relative roughness over D is equal to 0. You have to be careful in the problem because there are some statement there that is part of the solution. Then you have diameter is equal to 40 mm. Then the flow rate is 0.001 cubic meter per second. If it were to prevent turbulence from occurring, what would be the ratio of the head loss for the actual turbulent flow compared to that if it were laminar flow? Use dynamic equations. So, okay, so you have to get the ratio of the head loss. Okay, you have to find ratio of the head loss. Ratio to the head loss. Okay, head loss turbulent to head loss laminar. Okay, so we have here given the Q, the diameter, so you can get the velocity, which is 0.796. Then because you have already the velocity, you can use that in getting the Reynolds number, and it is greater than 2000. So that's why you have to use the Colebrook-White equation. Since your pipe is smooth, so what you have is only this, because it is already 0, no? So what you have is this formula from Colebrook-White equation. So substitute that to the formula, you can get 0.0194 for your F. Okay? You can solve this using calculators. You can solve this using some methods of algorithm, and you can do it a simple one, the trial and error. So if the value of the left side, the value of the left side is equal to the value, okay, of the right side are equal, so you can say that the trial value F is the correct value. Okay, the value of F is the correct value. Then you can substitute it to head loss, FLV squared over the 2G. So that is in terms, because we don't have the length, so you have this equation. This will be the equation in getting the head loss turbulent flow. So that is equal to 0.0157 times the length of the pipe. For laminar flow, you have F is equal to 64 over Rn. So substitute this to the formula. Your laminar now is equal to 0.00074 of its length. Okay, so you can express this also in percentage. So for the turbulent flow, if you're going to express this in percentage, so what gonna be the value? What gonna be the value? So for the head loss for turbulent flow is just equal to 1.57% of its length. So that's it. That is how you are going to interpret. Okay, then is that the then the other one, for the laminar flow, if you're going to express this into percentage, so you have 0.074% of its length. So if the length there is equal to 100, so your head loss in turbulent flow is equal to how much? 0.015, okay, 0.015 157, that is equal to 1.57 meters. Same as the head loss in laminar flow, that is equal to 0.074 meters. Okay, so I hope you got it, but the question is, what is the ratio? So the ratio is just equal to 21.216. Okay? Okay, for number 6, okay, given diameter is 300 mm. Sorry, that is rectangular, no? So that is, the area is equal to 300 mm by 400 mm. Okay, the pipe there is in rectangular shape, and Q is 150 liters per second. Assume F 0.025. So find head loss, okay, per km, per kilometers in length. So here the head loss per kilometer per length is just equal to so here you have, this is the solution. Okay, that is the solution. So from the formula, FLV squared over the 2G. Substitute, since the pipe there is not circular, so the diameter is just equal to 4R. Then hydraulic radius is equal to area of flow divided by the wetted perimeter. Since the conduit is rectangular pipe and it is flowing full, so that is the wetted perimeter is just equal to the perimeter of the square. Same also for the area of flow. The area of flow is just equal to the area of the square. Then the answer of D is 0.343. Okay, so since you have the area of flow and you also have the Q, you can directly 0.15 divided by 0.3 divided by 0.4. So your velocity is equal to 1.25 meter per second. Substituting it to the formula. So if your formula here is per kilometer, so you don't have this one. So the answer is 0.0058 meters per kilometer, or in 1 kilometer you have 5.8 meters, because in 1 kilometer it is equal to 1,000. I am right? 1,000 meter. 0, okay. So 0.025 times 1.25 squared divided by 0.343 divided by 2 divided by 9.81. So supposed to be, that is equal to 0.0058045 meters. So this will be, in that case, this will be meters per length if you will not include that one. But since it is said that this is the answer. The head loss over length is 0.0058 meters, or the head loss of 1 kilometer is equal to 0.0058 times 1,000. Okay, because there are 1,000 meters in 1 kilometer. So the answer is the same. You have 5.804. So 5.804. So because here you have, if you round off, no? Okay. That is 504. 0.04. Okay, so you can have different solutions, but you can still get the correct answer. Okay, for number 7, a square concrete conduit must transport 4 cubic meter per second of water a distance of 4 meters with a head loss of 1.8 meters. Find the necessary conduit size using the Hazen-Williams formula. So you need to find the what is this? Okay, the size of a square, no? So when you say square, equal sides. So this is the length. Assuming A is the length of the conduit and getting the velocity, you have this. Okay. Then your velocity formula for Hazen-Williams is that. So your answer is 0.788 meters. If you are required to determine the area of the area of flow, so just equal to 0.788 squared. So this is equal to 0.621 meter, meter squared. That is the area of flow. That is another parameter. If